So yes, so as you said, Andre, I gave a talk in the first series. I didn't know it was the first year. Back then, it was about event-triggered control, and this time I will talk about something which is completely different in terms of motivation. But I would say that the underlying tools share some common backgrounds. And so, in particular, in this presentation, we will talk about the estimation of some internal variables that are in lithium-ion batteries. And at the end of the day, we will come up with an estimator, which has a hybrid dynamics. And by hybrid, I mean that it exhibits both continuous time dynamics and discrete time dynamics. That's why we call it a hybrid dynamical system. Before I start, I would like to say a couple of things. The first one is that this work was mostly done by my former PhD student, Mira Khalil, who is now a postdoc at LS2N Centrale Nantes in France. We supervised Mira together with Stéphane Rael, who is a colleague in Nancy in electrical engineering. And Dragan Nezic was involved in this work as well. Mira spent some time in Melbourne some years ago. The second thing I wanted to say before really starting is that when Patrick and Andre contacted me, there were several options, several topics I could talk about. And I decided to go for this one for several reasons. I mean, the first one is more personal, is that I like to talk about batteries because it's something which is relatively new for me, I would say. And also it's an application and I work mostly on theory, so it's good to change from time to time. But more importantly is that in this applied work, I would say, or applied inspired work, ISS plays a key role in two aspects. Is that, as I already said, we will design an estimator. So this algorithm will generate estimated variables. And to assess the quality or the certification of the quality of this estimated variable, we will use ISS. So in particular, we will look at the mismatch between the estimated variable and the actual variable, and we will ask this variable to satisfy some ISS properties. But not only that, we also would like, behind this, the analysis, the Lyapunov analysis strongly relies on cascade ISS arguments. And not only, so we didn't first come up with the estimator and then manage to find a proof. It's actually the proof which inspired the algorithm. At some point, I saw that there was this cascade ISS interconnection, which was possible to put forward, and then we exploited it, and then at the end of the day, it ended up working. Okay, so now let's say a few words about the context and the objective of this work. So lithium-ion batteries, they are all around us, and it's not. I think it's fair to say so because these are the batteries that are on our cell phones, on our laptops, on electrical vehicles, and on many other devices. And this popularity is justified by the many advantages that lithium-ion batteries offer. The first one is that they have a lightweight. So when I say high, light, high, and things like that, it's always compared to other similar energy storage devices or technologies. So they have a lightweight. They also have a high weight and volumic power density. So what does this mean? That means if you take a unit, if you look at 1 gram somehow of lithium-ion batteries, it has a better power density than many other energy storage devices. Similar thing with the volumic power density. If we take 1 unit, 1 centimeter cube, for instance, of a lithium-ion batteries, the power density will be very advantageous. Also, it has a low self-discharge. So this means, for instance, in an electric car, if we let it rest during the night, the battery will not significantly discharge over the night and over even long period of time. That's really a good point. And the last thing that I like to mention, maybe by nostalgia, I don't know, is that they have no memory effect. So if you remember, maybe for some of you, the first mobile phone that were out there, the commercialized one, if we didn't charge them until the end, until they were fully charged, we would lose some capacity of the battery. And this clearly is not present in lithium-ion batteries in the sense that if I don't have time, I just charge by 10% more my battery, my phone, it's okay. I could still charge it up to 100% later on. So now there are no free lunches there. There are also some cons. First, their cost. They are not cheap compared to other technologies. They come with a cost. Even though this cost is reducing over time, still it remains significant. The second point, which is important, is the ecological impact of such technologies. Because not only we need to extract lithium, but also other elements which are rare, which are needed to build the positive and the negative electrodes. Because something that I will not dwell on too much during this presentation is that when we talk about lithium-ion batteries, there are actually many technologies. In all of them, lithium plays a key role, obviously, but there are many ways to design the positive and the negative electrodes. And the last point, which will serve as some sort of motivation, is safety. I mean, these batteries can easily, they might catch fire if they are not properly handled. There are, for instance, if we take a flight, one of the first questions that the staff on the airport will ask us when we check our luggage is whether we have lithium-ion batteries in our check bag, which is forbidden for obvious reasons, is that they might catch fire if they're not properly, if there is an issue with them. So to avoid this and to prevent the safety risk, these batteries must be deployed together with the battery management system. So let's say a few words about this guy. So what does the battery management system? First of all, it monitors what's going on in the battery. What do I mean by that? It looks at the available measurements provided by sensors, so typically some current, and voltage, and temperature measurements, but also some extra variables, like the state of charge. So this is the percentage that we see on our phones. Also the state of health, which is how old is the battery, and I will talk again about this later in this presentation, I think, and also various other quantities that are relevant. Why is it monitoring these quantities? This battery management system is to protect against safety risks. So what do I mean by that? Overcurrent, over voltage, and overheat. So basically, if we charge too much a battery, if there would be no BMS, the battery might catch fire. But also, if we discharge too much the battery, it's not good. It may accelerate aging. So the BMS is there. It's like if we discharge too much, it will cut the battery so that we do not accelerate the aging and we do not lose much capacity. So the thing is that this quantity that are needed to handle, to manage the batteries, the current, the voltage, the temperature, and the different states, only the first items are measured by sensors. The other ones, they are estimated. So this means, again, that when we look at the percentage on our laptop, on our mobile phone of our battery, it's not a measurement, it's an estimate. That means that behind this, there is an estimation algorithm. So mostly in this presentation, we will concentrate on the state of charge. And so let's say a few words, let's focus more on this guy now. So the typical approach to generate estimate of the state of charge, and I will use this common acronym SOC, SOC, is to use coulometry. So what coulometry means? It's really simple, I think. So it exploits this equation, which is satisfied by the state of charge. So the time derivative of the SOC, it's equal to minus 1 over the nominal capacity of the battery times the current. Okay, so how this equation can be used for estimation purposes? Well, simply by integration. So if you integrate this ODE from some time t-rest, and I will explain very soon why this is called t-rest, from some time t-rest to t, we obtain this equality. So SOC at time t is the SOC at the time t-rest minus the integral of this term from t-rest to t. And so I recall, is the current. This is like we consider it as an input to the system, and Q is the nominal capacity. So to implement in practice this equation, we need this. And what do we need in particular? The state of charge at t-rest. And why is it called t-rest? Because there are some operating regime where we can know from measurement, we can infer directly the state of charge. It's when the battery is at rest. It means if we have an electric car and we turn it off, after sometimes things will balancing out inside the battery. And by just looking at the voltage, the output voltage of the battery, we will be able to infer the state of charge. Okay, but if we use it, so if the current is non-zero, then we will need to integrate, and we can no longer do that. That's why we need this equation. And then we need to add this extra term, of course, for t greater than t-rest. And for that, we need to know the capacity. And the difficulty here is that this nominal capacity evolves with time. Because a lithium-ion battery, is not like a tank of a car. I mean, a car tank, if it has 60 liters one day, will have 60 liters in 20 years. For a lithium-ion battery, it's not like that. If it has a capacity at the beginning when it's produced, but later, as much as when it is used, at some point the capacity will shrink and we have less autonomy. I think we all know that, and we all have seen that with our phones and laptops. And also, to do this integration, we need to measure the current. So we do measure the current, but it's never perfect. That means that when we integrate it over time, we will possibly accumulate errors. So this says that if the battery is not too often at rest, this estimate will likely diverge and produce non-accurate state of charge estimate. And the fundamental reason is that this is an open loop technique. So we close the loop somehow when the battery is at rest, but most of the time it's just pure open loop integration. And it's not robust, as we all know. So an alternative to this is to resort to observer-based approaches, which are more closed-looped in nature. And for that, we need a model of the battery dynamics, and based on this model, we will design an observer, which is closed-loop because it will correct the estimates that it generates based on the measurements which are collected at any time instance. So there is an abundant and vast literature on how to design observers for lithium-ion batteries. But interestingly, the vast majority of this work concentrates on a single cell. While in practice, when we talk about a lithium-ion battery, it is on multiple cells. We talk of multi-cell battery or battery packs, as depicted in this picture, for instance. So then we could say, okay, so if I have n cells, maybe I could design one observer per cell. Okay, so if I have n cells, I will have an observer. And if each individual observer is of dimension n, then my multi-cell observer will be of dimension n times capital N. And when n is large, and it can be of the order of hundreds, like in electrical vehicles, this is going to be huge. And this is something we don't want to do in practice. So this is not a problem that I invented myself. It was raised to us by some collaboration, industrial collaboration that we have with a company. So this motivates an alternative approach where we like still to monitor what's going on in multi-cell batteries, but design through a low-dimensional estimator. Ideally, an algorithm whose dimension is independent of the number of cells. And this is what we will do in this work. So what's the catch? There is something we give up somehow by doing that. And then the idea is we will not try to estimate the SOC of all the cells, although as we will see, we actually do it. But our main motivation is really to estimate the minimum SOC among all the SOC of the battery pack. So this means we would like to know among all the cells which are interconnected, what's the value of the minimal state of charge between them. Why do we want to do that? Because it's super important when we discharge a battery to prevent aging. And similarly, we would like to know the maximum state of charge within a battery pack for safety reasons, because as I already mentioned, if we overcharge the battery, then it might catch fire. The tricky thing is that we already saw that the SOC, the state of charge, we cannot directly measure it. Okay, but not only that, here is that we do not know a priori which cell corresponds to the one with the minimum or the maximum SOC. Okay, so this is not available for measurement. So by the way, instead of talking about minimum SOC and maximum SOC, sometimes I will talk about limiting SOCs. That means either the cell has the minimum SOC or the maximum one. So how is this done in steel? Multi-cell batteries are all over the place. So how is it typically done? It's based on the heuristics, which is an assumption actually, which says that the cell with the limiting SOC are the cell with the limiting voltages. And why this is easier to do in practice, because we do not want to run one observer per cell, but we must measure the voltage of each cell for safety purposes. So even though we have hundreds of cells, there will be hundreds of sensors measuring the output voltage. But still, this is an assumption. Why? Because even if we look at the simplest model of the battery dynamics, we see that the measured output voltage is equal to this equation, okay? And this will be the case in the model that we adopt in this work. So if we would ignore all these terms, like if the output voltage would be some VOCV, so OCV means open circuit voltage, it doesn't matter. Let's say it's a nonlinear function of the state of charge of cell I. So if this equation would be true, then this assumption would be correct. Why? Because VOCV is a strictly increasing function most of the time for most technologies. Okay. But in practice, it's not true because we have extra term, a resistive term, another voltage, and of course, some measurement noise. So saying that the cell with the minimum SOC or the maximum SOC corresponds to the cell with the minimum or maximum voltage is not correct in general. Okay. So this has motivated results, new approaches based on observers. There are several references here which are provided, but none of them provide analytical guarantees on the accuracy of the generated estimates. Okay. It's just recently in this very nice paper by Zhang and co-author that they designed an interval observer addressing this question, and then they provide upper and lower bound on the unmeasured states. And briefly speaking, I would say we provide an alternative in this work, and each of our approach and this approach have their pros and cons respectively. I'll be happy to take questions on that later if you have any. So in this context, our objective is the following. We would like to estimate, given a battery pack interconnected in series, we would like to estimate the minimum state of charge and the maximum state of charge. Not only that, we would like our estimator to have a number of variables which is independent of the number of cells, so that it scales very well. And third thing, we would like that the estimates produced by the estimator are certified with some robust convergence guarantees. And that's where ISS will play a key role. So to design this estimator, we first need a model of the battery pack, or the dynamics of the battery pack. And for that, we model each cell dynamic by a so-called equivalent circuit model as depicted on this diagram. So it has one RC branches, one resistive term, and this voltage which depends on the state of charge of cell I. And the output of this cell is Vi, which is the sum with the right sign of all these terms. Okay. So by playing with Kirchhoff's law, we can quite easily obtain this equation. So the time derivative of this URC for cell I, it's equal to this equation, where tau di is the time constant of this circuit, and this is some nominal capacitance of this cell I. I is again the current, which is considered as an input, and we know it. We see again the dynamics, the equation for the dynamics of the state of charge of cell I, and then the output, which is measured, is the sum of all these voltages with the right sign. I didn't put the noise here, but I will add it later on. Okay. One thing is that in this presentation, to simplify a bit the exposition, there is only one RC branches. We can add the result have been developed actually for M RC branches. And we will see that the simulation results in one of the last part of this presentation that we took M equal 3. What's the interest of adding RC branches there is to improve the accuracy of the model. So now let's say a few words about this dynamical model and some assumption that we make on it. The first thing is we assume that these parameters, which are colored, are constant, and we know the one in magenta. So we know this capacitance, this capacity, and this resistance. Okay, they can be heterogeneous and they can depend on the particular cell that we're looking at. We do not need to know this time constant tau di. Of course, if we do not know it, this will have an impact on the quality of the estimator at the end of the day. But at this stage, tau di is free. The second assumption that we make is related to this nonlinearity that we have already encountered. So we assume that for any cell I, this function is known and continuous. And this is reasonable because typically we know that the open circuit voltage for the cell. It's typically given by a lookup table, and we can, of course, do a continuous interpolation between each point, and so that this first item is satisfied. But also, for most lithium-ion batteries technology, VOCV, the VOCV function also satisfies the strict monotonicity properties. Okay, so actually it's often more than continuous, it's often C1, and then it's essentially said that it's increasing with bounded derivative, to simplify. Here is an example of an OCV profile, a VOCV function, and we see that, of course, you have very steep derivative, but it's still bounded. It's not infinity here, and we can extrapolate it outside easily by basic techniques. And this sort of VOCV function will satisfy the assumption, that does satisfy the assumption that we saw on the previous slide. So now I think we are done with the model of one cell. So now, as I said, we're going to consider an interconnection in series of multiple cells. So we're going to have cell 1 up to cell capital N. And each cell has its own parameters and own function VOCV. Okay. And we measure, as I already mentioned, the output voltage of each of the cells for safety purposes. So to obtain a model of the battery pack, we just concatenate the model of for an individual cell. So I recall that the state of the cell I, denoted Xi, it's this voltage, URCI, corresponding to the RC branches that we saw, and the state of charge of cell I. And this vector is in R2 because we have two scalar variables. To define the global state, we just concatenate everything. So get X1 up to X capital N. That means that the state of the battery pack is of dimension 2 times N. The input is the current, is the same for all the cells because it's a series interconnection. And the output, the global output, is the concatenation of all the voltages which are measured for each cell. So V1 up to Vn. Here I've added plus F times V to model a measurement noise, additive measurement noise. We also add disturbances on the dynamics here. It doesn't cost much to do it in the analysis and goes through. So at the end of the day, by defining this variable and by playing by the equation that we saw before, we can write the model of the overall battery pack dynamics like this, with state X, and it satisfies this linear dynamics, and this with a nonlinear output function. Okay, and it's really nonlinear as we saw, where VOCV SOC is the concatenation of the VOCV of the SOC for each cell. Okay, so it's a fakely linear system, and this is really important. We cannot ignore it. So at this stage, if you would like to estimate X, it's not difficult to do because A has a great structure. It's diagonal. It's not Hurwitz because it has the SOC, so it has just an integrator, but we know how to design an observer directly for this system, and actually we will do it in the simulation part later for the sake of comparison. But we don't want to do that, because if we design a standard observer for this system, its dimension would be at least 2n. And when n is large, it would be too big, we will like something which scales better with the number of cells. And so, as I already mentioned, what we like to do is essentially to only estimate the SOC mean and SOC max. Of course, we'll estimate extra variables, but our main purpose are the minimum SOC and the maximum SOC. So formally, what do we mean by SOC mean and SOC max? It's just straightforward. Huh? The SOC mean at time t is the minimum over all the SOCs within the battery pack. And similar thing for SOC max. Okay, and that's what we want to estimate. We would like to know these quantities at any time t. One of the main challenges is that we do not know which cell corresponds to SOC mean and which cell corresponds to SOC max. Mathematically speaking, we do not know the min and the max. Okay, and even if we would know them at rest, for instance, it's not enough because they may change. It's not because one cell has the minimum SOC at a time t that it will have the minimum SOC in a time t prime greater than t. Okay, so we need a mechanism which is somehow able to detect which cell has the potential minimum SOC or maximum SOC. And for that, we came up with this hybrid estimator. So I will try to explain the reasoning just for the estimation of SOC mean, the same thing transpose for SOC max, as I will briefly mention later. So the first idea is to introduce some logic variable, sigma underline. So everything which is underlined, all the variables that we will see, they're related somehow to the estimation of SOC mean. For SOC max, I will use sigma overline. Okay. So sigma underline is a logic variable which will somehow tell us, oh, this is this cell which potentially has the minimum SOC. Okay. So given the value of sigma underline, we will design somehow an observer for the cell pointed selected by this logic variable. And this observer will generate some estimates of the URC, the local URC, and it will be denoted with a hat. So every estimate is with a hat. And an estimate of the SOC of the cell, and which we will take this as the estimate of SOC mean, which is denoted SOC underline hat. So I recall this is an estimate of the SOC of cells sigma underline. I've forgotten to put an underline here. There's a typo. And this will be taken as an estimate of SOC mean. Okay. So I recall that so far, the idea is what? We have a logic variable which tells us this is this cell which may have the minimum SOC. For this cell, we run an observer which provides estimate of the local variable, the local URC and the local SOC, and we take the local SOC to be the estimate of SOC mean. We will see how to do that. I do not hide all the details. Then the third point is, okay, we already mentioned that we will need to update the value of sigma underline at some point. Because again, the cell with the minimum SOC will not remain so over all the operation of the battery. It may change. So we need a mechanism which updates sigma underline. How do we do that? So for that, we will exploit the measurement that we have on the other cell. So the cell I, different from sigma underline. And here I recall the equation. So it's this nonlinear term depending on the local SOC, this resistive term, the term corresponding to the local ERC branches, the voltage of the ERC branches, and some measurement noise, which is denoted in this way. So let's rearrange this equation. We pass y, we flip this, we put it here, vice versa, and then we can obtain that VOCV of cell I at SOC I satisfy this equation. This function is invertible, so we can retrieve SOC I by this expression here. So I've put in blue the things that we know, and in magenta the things that we do not know. So what do we know? We assume that we know the VOCV function, so we can compute its inverse once for all, and then use it. Yi is our measurement of the output voltage of cell I. This is a resistive term that we know because we assume that we measure the current and we assume that we know this parameter. But we do not know the value at time t of the local voltage of the local RC branches, and we do not know the measurement noise. How do we cope with these issues? We do two things. We ignore the noise. We replace it by 0. If the noise would have some mean, we will put the mean here and the result will go through. But for URCI, what we will do, we'll use an estimate of it, denoted U hat RCI. But remember that we do not want to run one observer for one cell. So we need to find a trick to avoid running an observer for every cell, and yet that we will be able to generate estimate of the local URC, voltage of the local RC branches of cell I. And then the idea will be roughly, I will formalize it later more, that when there will be a cell I different from the current, the one we are looking at now, such that the local estimate of the SOC given by this expression is less by the estimate of SOC mean generated by the running observer, then we will update sigma underline. So these are the main ideas, and then we will see more formally how we do that. So I recall the model dynamics of URCI. It's given by this equation. Compared to the equation we saw before, I've just added a disturbance here. We can ignore it otherwise. Not so important. So what we propose to do is super simple. We say we need estimates of all the URCI. We need estimate of all of them because of this. We want to be able to compute this expression, so we need this. And for that, we will introduce some auxiliary variable, U bar or C, with these dynamics. What is important to see with these dynamics that they resemble those, but they are different in an important aspect, is that they are independent of the particular cell. There is no TODI, there is no CDI. It's just one TODI, which is a design parameter. And this guy is a scalar variable. And then given this dynamical system, I can already mention that we will be dealing with a hybrid dynamical system. There will be jump. A jump, this guy that will not change, whatever a jump means at this stage. Okay. So a jump, I can say actually a jump, it will be an update of the value of sigma underline or sigma overline. But when we change the potential cell that we're looking at, this guy doesn't change. It's purely continuous time dynamics. And given this auxiliary variable U bar or C, we will generate algebraically, so statically, estimates of the voltage of the RC branches of each cell in this way. So this is algebraic, it doesn't cost much to compute. So by just running one scalar dynamical system, we will generate n estimates through this algebraic equation. And what we can show is that if we concatenate all the URCIs in a single vector URC, and we do the same for their corresponding estimated variable, then we can easily show that they satisfy an ISS type property in this sense. That's the mismatch between the actual value of this vector, URC at time t, and its estimated version. It's bounded by an exponentially decaying term plus some perturbative terms. These perturbative terms are due to what? To the disturbance. This is not surprising, but also to D. And D is actually related to the error we do by picking tau D instead of tau DI. And this leads to that. Okay. So in the special case where all the tau DIs are equal and known, we can just set tau D to their value and this guy disappears. If we know the tau DIs, but they are heterogeneous, we can take the average value for tau D to minimize somehow, or the inverse of the average, and then we can minimize this term. I want to mention already, but in practice, this term is typically very small because URC is related to I, and for the value that we're looking at, we will see in simulation that this term will not significantly degrade the quality of the estimates. So this is the first time in this presentation that we incur ISS property. And we see that I already mentioned that we will be using cascade ISS argument. And yeah, it's clear. This system is living on its own. It will be part of the cascade. So now we have seen how to design the estimates of these URCIs. And we know that we can certify their convergence to some extent with some ISS properties. So now let's look at how we generate estimate of SOC mean. And then, the rationale is to say, okay, SOC mean is essentially the SOC of the cell pointed by this logic variable sigma underline. And we saw that we're going to call this estimate SOC underline hat, okay? How do we generate this guy? Well, we take a copy of the dynamics of the SOC of cell sigma underline, so this, that we correct with the linear term. L1 is a design parameter with L1 strictly positive, where this is the output voltage of cell sigma underline and its estimated counterpart, defined like this. So a very basic correction term. And we will see that the result works for any value of L1 strictly positive. So between two updates of sigma underline, SOC underline hat is generated with this equation. When there will be a jump, in particular, when we will need to update the value of sigma underline, we will update the value of sigma underline hat to the minimum of all the SOC I hat, where SOC I hat are generating using the equation that we saw before, the same one as before. And this we can again compute. This is measured, this we know, we measure I, and this is generating using the equation that we saw on the previous slide. Okay. So the last thing to do now is to say when and how do we update sigma underline. So sigma underline will be constant as long as this SOC underline hat is less than or equal all the other SOC high estimates. We just add here an epsilon, where epsilon is a strictly positive constant, to avoid the so-called Zeno phenomena. That means an infinite number of jumps in finite time. It's just some sort of regularization parameters. Okay, and when do we update sigma underline? Well, when there will be a cell for which the local estimate of the SOC beats SOC underline hat by epsilon. Okay, So we may criticize this because to check this assumption, it's an equality in practice, it may be tricky. I mean, it defines a set of Lebesgue measure 0. We can easily, thicken it in this way by adding an extra auxiliary parameter mu between 0 and 1, so that we will update sigma underline whenever we are in this region. So because this is easier to implement in practice, on the theoretical side, because of that, we generate non-unique solution, but it's not an issue at all because all the results that we will see apply to any solution of the corresponding hybrid dynamical system. Okay. So we do the same thing for sockmax. So for sockmax, we introduce some sigma overline. We use the same estimates of URC as before. We don't need to duplicate it. For the estimate of sockmax, it's denoted sock overline hat, and it satisfies this dynamics between two updates of sigma overline. So a copy of the dynamics of the sock of the local cell plus the same correction term, when L2 is also strictly positive. And when sigma overline will be updated, we update it according to this rule. And these guys are generating algebraically as we saw before. Okay, and then we have a similar update rule as we saw on the previous slide for sigma bar. So that when we bring all the things together, we obtain a hybrid estimator with these dynamics. So we have this auxiliary variable U bar RC, which is used to generate all the estimates of the URCIs. It has these dynamics. On flow, so these are dynamics on flow, so between two updates of the sigmas. These logic variables are constant, and the estimate of sockmin and sockmat are generated according to these two equations that we saw before. And this is true when we are in this region of the state space, which are just copy and paste of the condition that we've seen on the previous slides. What I would like to highlight here is that the dimension of this estimator, it's 5. It's 1, 2, 3, 1, 2, 3, 4, 5. But it's actually, I would say 3 plus 2 because the two variables are only logic variables. So they are really easy to implement in practice. That's why I wrote 3 plus 2. While the system we are looking at is of dimension 2 times n. So we do have an estimator whose dimension is independent of the number of cells. So at jumps, now we need to distinguish two types of jumps, whether we have an update of sigma underline or an update of sigma overline. So when sigma underline is updated, that means that when we think that the cell with the minimum SOC has changed, this guy doesn't change, U bar C. The value of sigma underline is updated according to the one minimizing the estimate of SOC I, and we correspondingly update the value of the minimum SOC, the estimated minimum SOC, while these two guys, they're related to SOC max, so they do not change. That's not their business. Okay. And similarly, we do the parallel thing. When we update sigma bar, this guy doesn't change. The variables related to SOC min are not changed, but those related to SOC max are updated according to these rules. Okay. So now with that, we're almost able to state the main results, just to specify at a high level the type of mathematical object we're looking at. So we cast the overall system using the hybrid formalism of Rafal, Goebel, Ricardo Sanfelice, and Ditil. So that at the end of the day, we write our system in this form, where Q is the state vector made of the state of the battery pack and all these estimated variables that we saw. Okay. This system is a special hybrid system because it depends on some continuous time input, U, which corresponds to the current, the disturbances, and the measurement noise. And we adopt the notion of solution that we have proposed recently, some years ago in a paper with Maurice Himmels, Pauline Bernard, Kunz, Karras, and Ricardo Sanfelice. I don't think it's so important for this presentation. What's more important, I think, is this main theorem which certifies the quality of the estimate somehow. So we already saw a lemma on how the URC hat relates to the URC, and here we go to the main point of this work is how SOC min relates to its estimate version. So here I just recall the dynamics of the estimate of SOC min and the estimate of SOC max on flows, just to highlight these parameters lambda 1, lambda 2. And the theorem says that we can pick any value of lambda 1 and lambda 2 strictly positive, any value that we use to regularize the jump dynamic, the jump map, so epsilon and mu, can take anything. Then there will exist 6 strictly positive constants, such that for any piecewise continuous input, this ISS type property holds. So what do we have here? We have on one side SOC min, so the quantity we are looking after, and its estimated value, SOC underline hat. And similarly, we have SOC max and its estimated value, SOC overline hat. And we can show that for at any time instance. So I should also say that here things are parameterized by 2 times. It's a feature of the hybrid formalism that we use. So T here denotes the continuous time, and J is the number of jumps or of updates of the sigma that's the solution has encountered. If you're not familiar with this hybrid formalism, you can forget about the J's and just keep focusing on the T. So the mismatch between these two guys is bounded by this term. We have an exponentially decaying term. Okay, I've forgotten to specify the E. I think E is the error between all the variables. C3 epsilon, so epsilon is this regularization parameter that we saw, but we can tune it as we want. It's just that the smaller it is, the smaller this term, obviously, but also the more jumps we will have, which is not necessarily an issue. We still have our friend here, D, that we saw before, related to the mismatch between the tau Ds and the tau Dis. And of course, some terms which are due to the disturbances on the battery pack and the measurement noise. Okay. And this is, to be a bit more specific, this is a two-measure ISS properties because we don't have the same argument here and there. This is not E, this is just SOC min and SOC hat and SOC max and SOC hat and the corresponding hat versions. How does the proof work? Well, we already saw that when we look at the mismatch between URC and URC hat, it satisfies an ISS properties with respect to some parameters uncertainties on the tau Dis and disturbances. Then we exploit standard cascade Lyapunov construction. We construct a Lyapunov function, which is the one that we use for this guy. And then we scale it by lambda. And then we add Lyapunov function for the estimates of this, the mismatch on the SOCs. Okay. And then what we can show is that on flows, we have these typical ISS type properties and at jumps, W doesn't increase. Okay. Then actually it's not over because based on these properties, we can derive a two-measure ISS property, but it involves not exactly what we want because we have an upper bound on SOC sigma underline and its estimated version, and similarly for sigma underline, while here we will have to have SOC min and SOC max. So to go from there to the property that we saw on the previous slide, we actually exploit the definition of the set C and D, the flow and the jump set, and then we can obtain the property that we saw. So that's what I mentioned at the very beginning of this presentation, that the reasoning and the proof are strongly inspired and rooted in this cascade ISS argument for hybrid systems, obviously. So now I will conclude with some numerical illustration. Oh no, I've forgotten something. I'm almost ready to conclude with a numerical illustration. Is that I recall that there is a noise affecting the output, and this guy may be tricky for some reason, but anyway. So if there is a noise, and depending on the properties of the noise, we would like to see what we can say about the inter-jump time. So we would like to know, for instance, whether we can have zero or not. And what we can prove under mild condition is that every solution to our system will have a so-called average or semi-global average dwell time. That means essentially that the amount of time between two jumps of a solution will be lower bounded by some constant. And so when V, this noise is modeled as a piecewise continuous function with a uniform bound on its maximum values, then we need to select this regularization parameter greater than V, some V bar times a constant. But when V is C1, with bounded derivative, we can take any epsilon. And in both cases, we can ensure that every solution has an average dwell time. So that essentially by this we avoid phenomena, but even more. Okay, so now let's look at the numerical illustration. So we took N equal 200 cells. And as I said in the battery pack model section, our result applied to a cells model with multiple RC branches. So to challenge a bit the simulation, we took an individual cell model with 3 RC branches, which means that at the end of the day, the dimension of the model for the battery pack is 3 times 200, that is 600. We took heterogeneous parameters among all the cells, with a 10% dispersion from a normal distribution, different OCVs for each cell. So how we did that, we took some nominal OCV and some envelope around them, and then we picked some function monotonically increasing in this gray envelope. We added a bias on the current that we measure. This is really realistic, and we didn't pick this on randomly. And this is based on physical consideration and practical consideration. Same thing with the noise. We have added some noise on the voltage that is measured of this type, and once again, these constants are not just made up. And we consider as an input a plug-in electrical vehicle profile, which is a typical type of input considered in the battery world, which has this form. So if I remember correctly, I think this is discharging, charging, and the battery is at rest. Okay, so a lot of variations. So to design the estimators, what we did, we took for the tau D, the average of the tau Dis. We assume that we know them, and we took the average value. For the correction term, L1, L2, we just took 10. I mean, we didn't have to really play much to get good results. The parameters to rule out 0 was set to epsilon equals 0.03. And this is just another regularization parameter to ease the testing of the jump condition, which was taken close to 1. And here's what we see. So let's have a closer look at that. So in blue here, we have the true SOC mean. So this is really the definition of SOC mean among all the 200 cells. And in orange, we see the estimator SOC mean, and we see that they are super close. Okay, and we have similar, except here maybe we have a small error. This will be clearer on the next slide. Same thing for the similar thing for the estimate of SOC max, which is depicted in SOC max in yellow, and in purple we have its estimated value. So we see that they fit pretty well. And we recall that the battery model is of order 600, while the estimator is of order 5, with including 2 logic variables. So if we plot the errors between SOC mean and its estimate and SOC max its estimate, we essentially see that we have an error after a transient of max about 2%, which is super reasonable in practice. Here there is a constant error at the end, a steady state error because of the bias that we have added to the battery pack model. So here, by curiosity, even though we do not say anything, we have plotted the index of the cell corresponding to the one with the minimum SOC or the maximum SOC, and the value of sigma underline. So this is our algorithm, which tells us, oh, this is typically maybe this cell with the minimum SOC, and we see that they match closely. But even if they don't match, I mean, they provide a good estimate of SOC mean. Same thing for SOC max. So what we did also is we wanted to compare it with a direct approach where we would design directly an observer for the overall battery pack model. So I recall here the battery pack model. I've forgotten to add the noise and the disturbance, but it's not so important. And for this, we can easily design an observer which converges, but this observer is of dimension 3 times n. So we would expect this observer to provide better performance results, but to be computationally more costly. And to evaluate this, Mira considered different values of the number of cells. So there is this huge table, so don't worry, I will not go line by one. I would just like to focus on 2 cases. When the number of cells is equal to 10, so a low number of cells, in which case we could, in principle, directly design an observer. What we see is that the computation time with the hybrid observer and the direct observer, they are similar. I mean, of course, it's lighter, but it's of the same order of magnitude. But also the errors. So the mean absolute errors and the root mean square errors on the SOC estimate, the SOC error estimates, they are the same order of magnitude, around 1% and 0.3. So they give similar results. Now, when we go to 1,000 cells, then things, in terms of performance, they are roughly the same. Of course, this guy is giving better performances, but not significantly better than those of the hybrid estimator. But in terms of computation time, there is no question. This is about 1 minute, 59 seconds, and here 4,000 seconds. So we clearly see here the benefit in terms of computation of the hybrid estimator. And to conclude, we wanted to compare with the standard approach in the industry, which is to, as I said at the beginning, that to say that, oh, the cell with the minimum SOC corresponds to the cell with the minimum voltage and vice versa for the maximum one. And we consider 200 cells for that. And so here we wanted just to see what's going on with the detection mechanism somehow. So in blue, we have the index of the cell with the minimum SOC. In orange, we have the values of sigma underline as before. But in yellow, we have the index of the cell having the minimum voltage, Vmin. And we see that this guy is changing a lot, which is not necessarily good in practice. And it can be easily explained by the noise. And we have a similar phenomena for the estimation of the max SOC. Okay, so this is the first argument against looking at Vmin and Vmax. Now, if we look now at the errors in terms of the estimate that are produced, so something I didn't mention. So, okay, with this approach based on the minimum limiting voltages, we design one observer for each of these cells. So, and we said that the SOC that they produce correspond to SOC min or SOC max. So these are the guys generated by looking at the minimum voltage and the maximum voltage. So when we look at the maximal thing, so the maximum voltage are depicted in purple and in orange. Essentially, our approach and this standard approach gives similar results. Maybe we do a bit better, but it's similar. But the approach is that the improvement is significant is related to the minimum SOC. Where the hybrid estimator produces the curve in blue, while the one based on the minimum voltage produces the value in yellow, and then we see a huge improvement of the order of several percent. And here we can even compute, evaluate to go beyond just graphical illustration. We see that for the SOC max, there is an improvement with the hybrid estimator, but it's not significant. It's much more significant for the evaluation of SOC min. We have 3% more accuracy with the hybrid estimator. So sorry, it was a bit long. I would like to conclude with a summary. So we have seen in this presentation a low-dimensional estimator for the minimum and maximum stock of lithium-ion battery packs in series. Importantly, this estimator is hybrid and its dimension is independent of the number of cells. And we've been able to certify the quality of this estimation using ISS property. And in particular, we could show some global robust convergence guarantees in terms of ISS. In case you would like to do more about this work and some extension, it's presented in this paper published in Automatica this year. And on our side, what we would like to do next, we already did some extension, but we are now working on the experimental online validation. And also we would be interested in adding some parameter estimation scheme, because here we assume that we know the parameters of the model. If we do not know them exactly, it's okay, because all what we've done is robust, but sometimes it's good also to add an estimation of some of these parameters because the value may change a lot. So thanks a lot for your attention. I hope this was clear, and I'm happy to take questions.